I would like to go over the proof for the general Leibniz rule using the principle of mathematical induction. The rule states that the nth derivative of the product fg is equal to the sum from k equals to 0 to n of n choose k times the n minus kth derivative of f times the kth derivative of g for all n in the set of whole numbers, which are the non-negative integers. And we have to assume as well that f and g are n times differentiable functions. Now, before I get started on the proof, notice something very interesting right over here. If we look at the binomial theorem, which has x plus y, or you can say a plus b, u plus v, whatever, to the power of n, and this is equal to the sum from k equals to 0 to n of n choose k, x to the n minus k, y to the k. And the proof for the general Leibniz rule is extremely similar to the proof for the binomial theorem. Okay, so let me just prove this rule now. So the proof is as follows. We're using induction, so we need the base case. Here, n is equal to 0 for the base case. And this implies that we have the 0th derivative of fg, which is just itself, f times g. And when we look at the sum from k equals to 0 to 0 of 0 choose k, the 0 minus kth derivative of f, the kth derivative of g. Okay, but this is just equal to 0 choose 0, and then times the 0th derivative of f, 0th derivative of g, and this is just equal to 1 times f itself times g itself, which is just f times g. Okay, so this implies that the base case holds. Now the second part is going to be the induction step. So suppose that the nth derivative of fg is equal to the sum from k equals to 0 to n of n choose k, n minus kth derivative f, kth derivative of g. Okay, for some arbitrary n in a set of whole numbers. Now, by the way, this right over here is the induction hypothesis. Let's look at the nth plus 1th derivative of fg. Okay, and this is equal to the nth derivative of fg. That, when we take that derivative, that will give you the n plus 1st derivative. Okay, so the derivative of the nth derivative will give you the n plus 1st derivative. Okay, and this is going to equal to the derivative of, now notice that we're going to utilize the induction hypothesis right over here. So I'm going to say that the nth derivative of fg is going to equal to this. Copy and paste. Okay, and this is equal to, now notice that when we take the derivative of a sum, the derivative of the sum is the same as the sum of the derivatives. So this will be the sum from k equals to 0 to n. And then we're going to take the derivative of each term. N choose k, f n minus k, g, k. All right, and then that derivative, which is equal to, now I'm going to apply the product rule over here. Now n choose k is going to be a constant, so that could be factored out of the square brackets. So we have product rule utilizing on these, it's going to be the derivative of my first guy times the second guy plus the first guy times the derivative of the second. So now what I'm going to do is that I'm going to split this into two sigmas, okay, right over here at the plus sign. So this is going to equal to sum from k equals to 0 to n choose k, f n minus k plus 1, gk, okay, and then plus sum k equals to 0 to n choose k, f n minus k, g, k plus 1. Okay, now what I'm going to do is that I'll take this second term over here, and then I will have a change of indices, except that I'm going to start from k equals to 1 to n plus 1 now, which means in the sum end, k's become k minus 1s. So then this will be n plus 1 minus k, okay, because what we're going to do is we're going to do n minus k minus 1, which is the same thing as n minus k plus 1, which is the same thing as n plus 1 minus k. Okay? Then right here I have gk. All right, cool. Now what I'm going to do is that from the first expression over here, this first sum, I'm going to pull out the k equals to 0th term. Okay, so I'll get n choose 0, then f n plus 1 g0, and then plus, and then what I have remaining is from 1 to n of the rest. And then plus, and then from here, this sum, I'm going to pull out the k equals to n plus 1 term. So this will be k equals to 1 to n now. N choose k minus 1, and the rest. Then adding the n plus 1th term is going to be n choose n plus 1 minus 1, which is n, f, and then n plus 1 minus n plus 1 is going to be 0, then g, n plus 1. Okay, very nice. So now, these two could be combined because both of them run from 1 to n. Now, right over here, we're going to combine it. So we're going to have this expression for both of them, which can be factored out. So I'll get n choose k plus n choose k minus 1. Okay? And then f n plus 1 minus k gk. All right. Now, once again, n choose 0. This is equal to 1. N choose n. This is equal to 1. Anything choose 0 is 1, and anything choose itself is 1. All right, so I'm going to make this to be n plus 1 choose 0, which is still 1. And then this part right over here, I'm going to use Pascal's rule. And this will become n plus 1 choose k. And then right over here, this will be n plus 1 choose n plus 1. Okay, it's still going to equal to 1. So I changed it to look like this form because notice that when I plug in k equals to 0 into here, I get this part. And when I plug in k equals to n plus 1 over here, I get this part. So essentially, all this boils down to is the sum from k equals to 0 to n plus 1 of n plus 1 choose k, f n plus 1 minus k, gk. All right, and this is good. This implies that the induction step holds. Okay, we got it into this form. So therefore, by the principle of mathematical induction, the nth derivative of the product between f and g, okay, is going to equal to the sum k equals to 0 to n of n choose k times the n minus kth derivative of f times the kth derivative of g for all n in the set of the whole numbers. And this completes this proof.